Good afternoon. And today we're going to talk about the first law of thermodynamics for a closed system, and then we'll do a couple example problems as well. Like I said to the 8:30 class, it looks like you can come whenever you want to class. You don't hesitate to attend as long as you can. And I don't know how much longer this is going to last for us, but if you feel comfortable, please come. I have high hopes, but we'll see how everything ends up showing up after numbers come out this week. Okay, first law of thermodynamics for a closed system. What is it? You should have this at some point memorized because you're going to be using it so much. The change in kinetic energy plus the change in potential energy plus the change in internal energy is going to equal the heat transfer minus the work. Okay, that is for any closed system. This is the first and most fundamental law that needs to be applied to it. Now, I'm going to give you some things I want you to think about with this, and then we'll actually use this equation to solve a couple problems here. The first thing is everything over here on the left-hand side of the equation is stored energy. Okay, it's inside the system. Kinetic energy inside the system, potential energy, and internal energy. Everything over here on the right-hand side, this is transferred. Okay, this goes in and out of the system. Okay, and all we're caring about is by looking at the boundary. So everything on the left-hand side, this is a property. Okay, this is why we can do 2 minus 1, kinetic energy at state 2 minus the kinetic energy at state 1. We can always set that equal to that. All right, so when I am looking at problems that I'm going to be dealing with in this class, often my kinetic energy, my potential energy, I can assume these are negligible or they go to zero because the kinetic energy changes of many of our problems are going to be on the magnitude of like 1 or 2 or 3 joules. Whereas everything else we're going to be dealing with is in kilojoules. Yes, there is some, but it's not significant enough. And so unless a problem tells you specifically, here's some velocity of the system, or here's some height change of the system, ignore it. Internal energy is going to be something that we're going to deal with a lot. So again, internal energy is the energy of the molecules inside the system. So if this is my system here, this little hand sanitizer container, kinetic energy would be if it's moving around. Potential energy would be its height change above a datum. And then the internal energy is just internal to that system. How are those molecules moving? And in chapter 2, we're going to tell you the information about that internal energy. In chapter 3, then we're going to ask you to go out and find that energy. When we're talking about the transfer, Q and W, we're now concerned only about the surface. So I'm basically going to consider myself to be this plastic container. And I don't care what's inside the container. I don't care if there's hand sanitizer, or if there's water, or if there's just air. I don't care. I just care what is crossing my surface. Does it look like work is crossing my surface? Great. Does it look like heat is crossing my surface? I have to look down and just see what's crossing. That's all I care about. And so we have to keep that perspective in mind when we're looking at these problems. Okay, so that is the first law of thermodynamics. We're going to use it today. We're going to talk on Wednesday in class. We're going to do what Monday or today's lecture is, and so we'll focus a little bit more on heat transfer, but we're going to go right back into it on Friday to make sure that we really understand this, and so it's going to be a big part of your first exam. Are there any questions about this equation? Okay, so let's do 2 example problems, and here's what I did this morning. I chose 2 example problems like at 8:15. I thought, you know what? I'll just choose 2 example problems. And I chose one, was pretty good, and I chose a second one, which was an utter disaster. And we'll talk about the issues with that problem here later. So let's go and I'll show you what the first problem is. Okay, so the first problem we're going to be dealing with is this one. It's going to say 4 kilograms of carbon monoxide, CO2, is contained in a rigid tank with a volume of 1 meter cubed. The tank is fitted with a paddle wheel that transfers energy to the carbon dioxide at a constant rate of 14 watts for 1 hour. During this process, the specific internal energy of the carbon dioxide increases by 10 kilojoules per kilogram. If no overall changes in kinetic and potential energy occur, determine. Okay, now even though this said this in the problem statement, I need to restate this or save this for my assumptions. Okay, because this is an assumption. They're telling you what the assumption is. So what does this problem tell me? It tells me mass, 4 kilograms. It tells me material, carbon monoxide. That doesn't really matter much here in chapter 2, but it will matter a lot in chapter 3. We know it's a rigid tank, and we know the volume of that tank. We know this tank has a paddle wheel, and we know the paddle wheel transfers energy to the carbon dioxide, so from the surroundings to the system at a rate of 14 watts for a time of 1 hour. And when that happens, because we're transferring energy into that system, the internal energy of the carbon dioxide increases. Okay, so this all makes sense, but I think we need to spend some time trying to understand what the problem statement is trying to tell us. All right, now, I have to move that off the screen. No, I guess I can do this. I can do this. The reason I have to do it this way is because the recorder on this screen only records the far screen over there. So I want to show it up there for a little bit, then I'll put it back over here so we can see what's happening in class. All right, so let's write down what we know. Okay, we know that the volume of the tank is equal to 1 meter cubed. We know the mass is equal to 4 kilograms. And so if we draw a picture of this, we're going to draw a rigid tank. So it's not a piston cylinder, a rigid tank, closed system. And we're going to put a paddle wheel inside of it, a mixer that's going to be inside of this. Okay, so we're going to say carbon monoxide, sorry. All right. Now, we also know that U2 minus U1, or the change in specific internal energy, is going to be 10 kilojoules per kilogram. Okay? And we know that the rate of work, it says here in the problem statement, at a constant rate, transfers energy at a constant rate of 14 watts for 1 hour. So we know that our rate of work, which is equal to W dot, is equal to 14 watts. And the time, the delta T that it acts, is going to be 1 hour. Okay? They want us to find the following things, A, B, and C. The specific volume at the final state in meters cubed per kilogram. Okay, so let's try to find A. What is the specific volume in meters cubed per kilogram? Well, really, the units are telling us what we need to do here. Okay, we know the volume is 1 meter cubed, and we know the mass, and that is 4 kilograms. And so this answer is going to be 0.25 meters cubed per kilogram. Dead easy problem. But let's look here what it says. It says the specific volume at the final state in meters cubed per kilogram. They asked us specifically for the final state. What's the specific volume at the initial state? Anybody? It's exactly what I have up there? Is that what you said? Yeah, it is. Because the volume at the initial state is still 1. The mass at the initial state is still 4. It's still 0.25. So they're asking us something about the final state, but it's the same thing. Now, that may make total sense to you. The volume doesn't change, the amount of mass doesn't change, so the specific volume shouldn't change. Remember this, because while it's very obvious here in a problem, in chapter 3 when we're starting doing problems, whenever you see a rigid tank, you're going to know that the specific volume does not change between 1 and 2, and that is going to be a hint or a clue to give you some information that you need to do to solve the problem. It's hidden inside the problem statement when it says rigid tank. Okay, so I want to emphasize that. Okay, now, Part B, what does it ask us for? In Part B, it says the energy transfer by work in kilojoules. Okay, now, we can do this a couple ways. You can just look at that and say, well, they told me 14 watts, and I know what a watt is. A watt is equal to 14 joules per second. So if I could, it wants it in kilojoules, if I just took how many seconds times this 14, I would get my answer. You could just look through the units there. That's one way to do the problem. Let's do it more formally. We know that the work is going to be equal to the integral from time 1 to time 2 of W dot dt. That's the official way to do this. And we're going to say that the work is constant. Okay, they said it's 14 watts for 1 hour. That's constant, so that comes out of the integral. And so we're just going to have W dot times T2 minus T1, which gives us the same answer that we did before, but now it's just formally walking through the integration process. Now, let me ask you a question here. When I put this in here as W dot, I put this as 14 watts. Is that going to be positive or negative? Speak up a little louder with your masks. Let's read what the problem statement says. It says, during the process, the wheel is fitted with a paddle wheel that transfers energy to the carbon dioxide at a constant rate. Well, let's make sure we didn't do this up here, but what is my system? My system is the carbon dioxide. I should officially make sure that's my system. So is this positive or negative? It should be negative. The surroundings are acting on the system. Something outside of the system is spinning that paddle wheel, and that's putting energy into the system from the surroundings. The system is not creating the 14 watts, something outside. So that's going to be a negative. And then we're going to have our time 2 is going to be 1 hour, and our time 1 we're going to see is 0 hours. Okay, now we have to work with our units here. This is going to be negative 14 watt is a joule per second times 1 hour. And we know here that in 1 hour, there is 3,600 seconds. Or you can say in 1 hour, there's 60 minutes, and in 1 minute, there's 60 seconds. That's 60 squared is 3,600. Okay, so let's look at our units here. Hours cancel, seconds cancel. We're going to have units of joules, so let's put it in our calculator. Minus 14 times 3,600. And we get minus 50400 joules. The answer they want is in kilojoules, so we move the decimal place over 3, and we're going to get minus 50.4 kilojoules. That is our answer. Now, they ask us specifically here, the energy transfer by work. Sometimes Wiley says things such as, how much work is added to the system. There, Wiley is telling you work added to the system. They're already saying we know it's negative, so just give me the magnitude. Sometimes they ask the question is, what is the energy transfer by work? That you need to know sign with it. So be careful. Sometimes the students say, I've been trying this forever. I can't get the right answer, Dr. Wanklin. And I'm saying you have the right answer. You're just inputting it into Wiley wrong. Okay, you just input it. You're not putting it in with the right sign. Part C, it says the energy transfer by heat transfer in kilojoules and the direction of the heat transfer. Okay, so with that, what we're going to do is we're going to type in our first law, KE plus delta PE plus delta U is equal to Q minus W. We can, in certain cases, calculate heat transfer directly, but most times in this class, we're going to solve for everything else and get out what our heat transfer is. And so the kinetic energy and potential energy they told us to neglect. We were given the change in specific internal energy, and we've been given, or we calculated the work so we can find everything else. Okay, what we're going to have here is mass times U2 minus U1 is equal to Q minus W. Okay, so our mass, we had 4 kilograms. 4 kilograms. Our U2 minus U1 is 10 kilojoules per kilogram, is going to equal to Q minus 50.4 kilojoules. Correct or incorrect? Incorrect. Why? Yeah, I need to put this parentheses here, and I need to put a negative sign here. Another common issue. Students won't put that negative sign in there. That's why I put that parentheses there. It's a negative, or a positive that we'll be dealing with here. So I'm going to have 40. Well, I move to the other side of the equation, minus 50.4. So what I'm going to end up with is the Q is going to be equal to minus 10.4 kilojoules. Does this mean heat is added to or removed from a system? Removed from. When we add heat to a system, it's positive. When we remove heat from a system, it's negative. When we add work to a system, it's negative. When we remove work from a system, it's positive. Make sure we know that sign convention. Make sure we can get that. Are there any questions here with this problem? Not a bad problem. Easy math. Just have to make sure we have the thermo part of it. Okay, now let's look at the next problem, which is a problem that I have I've already sent a letter to the publisher because I don't like the problem at all this morning. I'm going to change this to here. Okay. They say this. Figure shows a gas contained in a vertical piston cylinder assembly. The vertical shaft, whose cross-sectional area is 0.8 centimeters squared, is attached to the top of a piston. The total mass of the piston in the shaft is 25 kilograms. Notice this looks like a problem that you've done already in chapter 1 when we talk about pressures. That's why I chose it today to do today. While the gas is slowly heated, the internal energy of the gas increases by 0.1 kilojoules. The potential energy of the piston shaft combination increases by 0.2 kilojoules. And the force of 1,334 kilojoules is exerted on the shaft as shown in the figure. Okay, now he says this. This is where this problem starts to get messed up here. The piston and cylinder are poor conductors. What does that mean? There's no heat transfer. That's how I read it. If you say that the piston and cylinder are poor conductors, I'm thinking that's poor thermal conductors, there's no heat transfer. However, they say it right here on the top, while the gas is slowly heated. Well, how? I don't know how it's slowly heated if it's poor thermal conductors. So I don't know what's going on here. This picture actually shows heat coming into it, so I don't like it at all. That's one other thing. And then it asks us to, it says, and then the friction between them is negligible. The local atmospheric pressure is 1 bar and gravity is 9.81. Then it wants to determine the work done by the shaft, the work done in displacing the atmosphere, and the heat transfer for the gas. Okay, I'm going to change the way this problem is asked because we're never going to do in this class the work done by the shaft and the work done by displacing the atmosphere. We're going to do this slightly differently. We're going to find out how much work the gas does. Okay, we're going to find out how much work the gas does, and then we're going to pretend like this thing that wasn't said, that we have poor thermal conductors, and we're going to try to figure out how much heat is added to the system for that to occur. That's what we're going to find. Okay, so let's do that this morning. Nope, that's not what I wanted to do. There we go. So in this problem, it's hard to itch your nose with a mask on. And lick your finger. I keep wanting to lick my finger. This is not things you should be doing when you're in the middle of a global pandemic. Okay, so here we go. Here is our piston cylinder. Let's draw a free body diagram. We have this piston cylinder here. It tells us the area of this is 0.8 centimeters, and it tells me the diameter of this is going to be 10 centimeters. It tells me outside here is going to be 1 bar, I believe. 1 bar. And then it tells me there's a force coming down here on the top of this of 1,334 newtons. And it tells me that the change in potential energy of the shaft and the piston is equal to 0.2 kilojoules. And it tells me that the change in internal energy of the gas is equal to 0.1 kilojoules. Okay? And what we want to figure out is what is the work being done and what is the heat transfer. Okay, we want to know these two things. Okay. They also tell us here the mass here is equal to 25 kilograms. Okay. So what we're going to do in this problem first is find out what are our forces, because we need to find out for the work equation is going to be, the work is the integral of P dV, okay, the pressure inside times the volume change that happens there. Now this problem statement didn't tell me a volume change right away. It just didn't directly tell me that information. And it did, but the other question is, did it tell me what kind of boundary work mode I'm undergoing? Because we have a couple choices here, right? We have constant volume. Well, we know there's not constant volume. It's a piston cylinder. We have constant pressure, and we have polytropic. So we go back and we read our problem statement, and we say, is there anything that says that it's polytropic? And it doesn't. It doesn't say N is equal to something. It doesn't say PV is equal to something. It doesn't say any of that. So we're going to assume that pressure is constant. The other thing they say in the problem statement is that the friction between the piston and the cylinder is negligible. It's really smooth movement up and down. So we're going to assume constant pressure work. That's what we're going to work with. But we don't know the pressure inside that piston, and we don't know how far it goes, what the volume is. So let's find that out. So what we're going to have here in our force balance is coming down, there's going to be a force of 1,334 newtons. There's also going to be a force coming down of mg. Okay. There's also going to be, and we have to worry about this shaft here, there's also going to be a pressure, atmospheric pressure acting on the outside of this, pushing down. This is going to be P atmosphere times the area. And remember, they're going to consider just that area, this area here, this donut area. They're not going to worry about the top of that shaft. What is counteracting that? Well, pushing straight back up, all down here, pushing up, this is going to be the pressure of the gas times the area, and this is going to be the area on the whole entire bottom of that piston going up. So we should be able to find out what the pressure is by doing a simple force balance, and you're going to have to do this multiple times this semester, so might as well get that practice done. So coming down, 1,334 newtons plus mg, they said it was 25 kilograms, I have to get 9.81 meters per second squared. Also, the pressure of the atmosphere, they said, was 1 bar. And now we have to worry about this area here. Well, the area is going to be pi over 4 times 10 squared minus 0.8, and this is going to be centimeters squared. So here I took the area of the overall circle, I subtracted the area of that shaft, and it's in centimeters squared. That has to equal the pressure of the gas times the area, which is going to be pi over 4 times 10 squared, and this is going to be centimeters squared. Now, I have a small problem here when I get started because my units aren't going to work out. The first is in units of newtons. We're good. The second, kilogram meter per second, this is units of newtons. We're good. But now we have bar centimeters cubed. And that's going to be a problem. So I'm going to start calculating these things and put them together, and we'll go through. So I'm going to do 1,334 plus 25 times 9.81. Okay, 1,334 plus 25 times 9.81. This first term, two terms are going to give me 79.25 newtons. Okay. Then plus, let's see what this is going to be. Pi over 4 times 10 squared minus 0.8. This is going to give me 77.73 bar centimeters cubed. And I have to say, how do I get that into the right units? Well, I know that 1 bar is 10 squared kilopascals. Okay, 100 kilopascals is 1 bar. And I also want to do here, I want to get centimeters. I want to say that 100 centimeters should be squared here, not cubed. 100 squared centimeters squared is going to be 1 meter squared. Okay, what does this do for me? Now, this gets rid of this centimeters and this centimeters, and I have kilopascals times meters squared. Well, a kilopascal is a kilonewton per meter squared. So when I cancel my meter squared, I'm going to have kilonewtons in this. Kilonewtons times kilonewtons added to newtons is not going to work, because I'm going to have to move this to newtons here. So I'm going to say that in 1 kilonewton, there's 1,000 newtons. And now I can add everything else together here. So I have to pay real close attention to those units. Really, really close attention to those units. And so what do I get here? I have 77.73 times 100 divided by 100 squared times 1,000. And I'm going to get, make sure I got that right, 77.73 times 100 divided by 100 squared times 1,000, 777.3. Okay, I add that to the 1579.25, and I'm going to get 2,356.55 newtons is equal to the pressure of the gas times, well, what do we have here for the area here? The area is going to be pi over 4 times 10 squared. This is going to be times 78.54 centimeters squared. I'm again going to have to convert here that there's 100 squared centimeters squared in 1 meter squared. So I'm going to get 2356.55 newtons is equal to pressure of the gas times 78.54 divided by 100 squared. Should be able to do this in your head, I guess. 0.007854 meters squared. And so the pressure of the gas is going to be 2356.55 divided by that previous answer. 300,044 newtons per meter squared, which is a pressure, newtons per meter squared. I can write this in terms, I can write this as 300 kilonewtons per meter squared, or 300 kilopascals. Or how many bars? Three bars. Okay, so this is, I think this is actually what the number they gave to you in the problem statement that you had back in the first chapter. So now I know the pressure. I know the pressure inside of that. What is going to be the volume change? How do I find the volume change here? It didn't give me anything about volume. What do I do? Is this, let me see if you can answer this question. Is this piston cylinder, is it expanding or contracting? Why do you know it's expanding? It's being heated up, okay, it's being heated up, that's fair. But there's something else in the problem statement that says it's expanding, because it's being heated up. Okay, there's a change in energy inside the system. You're going to say the energy inside the system is going up by 0.1 kilojoules. That's correct. That's another thing. But the energy could go up, the internal energy could go up without any volume change. If you look at the potential energy of that shaft plus the piston, it's a positive 0.2 kilojoules. That means that piston has to increase its potential energy by moving up. Okay, so we know the potential energy of that's moved up. If I can figure out how far that piston moved up, that's going to be an x distance. I also know the area of that piston. The area times that x distance will give me a volume. Give me a volume change. So that's what I'm going to do here. So I'm going to say here that the potential energy is equal to 0.2, I think, 0.2 kilojoules has to equal mass times gravity times Z2 minus Z1. Okay, so 0.2 kilojoules is equal to the mass, which is 25 kilograms, times gravity, 9.81 meters per second squared, times Z2 minus, let's just call Z1 0. So we're going to see how far we move up. All right, now, what do we have here? What is a kilojoule? A kilojoule is a kilonewton times a meter. Okay? Here we're going to have kilogram meters. We're going to have newtons times meters. So we're going to have to say that there are 1,000 newtons in 1 kilonewton. Okay, so let's solve here for what Z2 is. So we get 0.2 divided by 25 divided by 9.81 times 1,000. And we get that our Z2 distance is equal to a positive 0.815 meters, which is a heck of a distance, right? Almost entire meter of change of this piston. That's a lot. A lot. I have some problems with that too, with this problem, but we'll leave it to where I am. Okay? Now, if I can take this times, so that our volume is going to be Z times our area, so 0.815 meters times pi over 4 times 10 squared centimeters squared. And again, 100 centimeters squared is 1 meter squared. We're going to get the volume change of times pi by 4 times 10 squared divided by 100 squared. We're going to get a volume change of 0.0064 cubic meters. Not very much. Okay, we have a very 10 centimeters. We have a 10 centimeter piston that's moving about a meter in height, which is just ridiculous, but anyway. Okay, so now we can find out what the work is. The work is the integral from 1 to 2 of P dV. Pressure is constant, so this is going to be pressure times V2 minus V1. We said the pressure was 300 kilopascals. V2, we're going to say 0.0064 meters cubed. We're going to consider our volume 1 to be 0, and that's going to give us our delta B. Okay? Kilopascals times meters cubed. Remember, a kilopascal is going to be a kilonewton per meter squared. We're going to be putting these things together, and a kilonewton times a meter is going to be a kilojoule, and that's exactly what units we want. And so if I do that, I get 1.92 kilojoules. Now it told me 1.92 kilojoules, and it's a positive. Is that correct? Well, the first thing is, whenever I do the integral of PdV, it always gives me, the sign convention should be out correctly, so I don't have to worry about it. But I just have to make sure it logically makes sense. If that piston is moving up like this, what's happening is the gas is working on the surroundings, and so I should get a positive value. So 1.92 kilojoules is correct. Now, he wants us to continue with this problem and find out how much heat has added for this to occur. Now we go to our first law. Delta KE plus delta PE plus delta U is equal to Q minus W. Okay, they told us that the kinetic energy and the potential energy are negligible. But you might ask this question. Let me ask this question right now. Students ask this question to me all the time. Okay. There is a potential energy change of that piston because it's moving up. Why isn't there a potential energy change if my system here is my gas? System here is the gas. I understand why there's no kinetic energy change of the gas because it's not moving with any velocity. But why isn't there a potential energy change for the gas? Okay? Because that gas, if we look at it here, that gas is moving, I'll change the color here. From 1 to 2, if you look at the system here, our system will have a center of mass here and a center of mass here of that gas. The center of mass of the gas does rise a little bit because of the expansion. So really there is a potential energy increase of that gas. But the mass of that gas is so small that the mass times gravity times the little change in Z is negligible. And that's why we say it's negligible up there when we deal with gases. Now, when we have something heavy like a piston, 25 kilograms, yeah, now there's going to be potential energy is probably going to be something that we need to think about. But that's why we neglect potential energy change. Even though there is one, we neglect it. Okay? All right, so what else do we have here? We have delta U. They told us in the problem statement that the change in internal energy is 0.1. As the gas is slowly heated, the internal energy of the gas increases by 0.1 kilojoules. So we have here 0.1 kilojoules is equal to the heat transfer minus the work we had, which is 1.92 kilojoules. And so, if we want to figure out what is the heat transfer is going to be 2.02 kilojoules. And it's positive, which means that heat is taken from the surroundings and added to the system, which is exactly what we expect it to be. Now, I don't know what nonsense they're asking to us in this other problem. They're asking some stuff to try to make us confuse us a little bit, and it confused me. I will tell you one thing for darn sure this morning. I came into class cocky, thinking I know what's going on. I taught this class for 10 years. I know what's going on, and I saw this problem, and I was in the wrong mindset, and I got myself all confused. We worked through it a little bit, but it didn't give the 830 class any confidence. So what I want you to make sure that you can do is you can kind of walk through things this way, and I'm going to try to make sure that I make problem statements that are clear. You know, if I say it's a poor thermal conductor, that means there's no heat transfer. And if you can't understand from the problem statement to the solution, if you can't understand why something's happening, you need to ask me. If Wiley shows a solution that you're like, I don't know what's happening, let me know. Because that is where this class could be won and lost. Okay, so make sure that we follow along with that. Are there any questions about this type of problem? You're going to be doing lots of problems like this. Lots of problems like this. It's going to have multiple steps. Finding power, finding pressure, finding work, putting that into the first law. And then we're going to add in this part in chapter 3 where now we're going to remove this internal energy and you're going to have to find that whole thing. So I can give you this problem one more time. And you can find it again one more time in one more way. Okay? We are in class on Wednesday. What we'll be doing is solving some problems with the modes of heat transfer. We'll be actually directly calculating the heat transfer. And then on Friday, we'll be doing, again, some more things with the first law when we're dealing with systems. Okay? Homework is looking like it's going pretty well. We had some issues with, I didn't prepare Jennifer very well. Jennifer has graded for me and another professor. She graded for me last fall, and I thought she would remember how we did things, and she just forgot, and so I should have made sure. So we had some grading errors. So make sure that the grading is exactly what you expect on the homework. We have 2 weeks from today, we have a exam. I'm going to make a decision at the end of this week about how the exam will be run, depending on how many students I have quarantined and what we need to do here, because I want to make sure that you all have the same thing. What I will promise you is that if the people at home have an open book exam, the people in class will have an open book exam. Okay, I'm not going to require a different calculator because I require that at home. I have too many quarantine students to worry about that. So everybody will have the same thing. You will either take it with me or you'll take it at home. And I know there is the potential that the people at home have, they have internet and I'm going to try to work around those issues right now. But hopefully, the idea is for you, that those of you who want to take it in person and want to do it at home can do so and have the same experience. That is assuming that we are able to hold classes on campus. If we can't hold classes on campus, then you will all take it at home, and then we'll work out that as we go. So I'll keep you informed as we get going through there. Okay? Until then, have a good rest of your weekend. Good rest of your week, and we will see you on Wednesday.